Hello everyone, this will be an update on our milestone 4, which is the interpretation and communication of insights. For those who haven't seen this video, this is about our data mining assignment, which is on predicting crude palm oil prices and the production yield from climate data and news sentiment. So this is a GitHub link where you can read more about it. Going to our Jupyter notebook, basically this time we have done all the cleaning of the data and everything. We have the hypothesis, which is that the weather data can significantly affect the palm oil production yield, as well as the second one, which is the news sentiment can also affect or correlate to CPO commodity prices. We have four major sources of data set here. One is the weather data, the other one is the news data scraped from the edgemarkets.com. The third one is a production data, which is a monthly data from Malaysia. And the fourth one is the commodity price for CPO in Malaysia Ringgit. Malaysia Ringgit is used to minimize the forex effects because we can have a lot of fluctuation with the exchange rate between MYR and USD. So while the data is clean, we still do some just minor data wrangling, like renaming the columns, standardizing the data, timestamp, converting the type, and so on. So this is just some minor stuff. If we can jump straight into the exploration of the data, here we have the CPO price. This is based on the trading days, on the close price of the trading day from 2014 to early 2020. And we have also the CPO production. This is on a monthly basis by Malaysia statistics, the palm oil statistics called MPOC. Okay. So as you can see here, there isn't much correlation between the price of the palm oil and the production of the Malaysia palm oil. Next, we look at the weather data. These data are 106 weather stations from Malaysia, Indonesia, and Singapore. But this time we'll be mainly just looking for weather stations in Malaysia because we are predicting the palm oil production from Malaysia as well as the crude palm oil prices in Malaysia Ringgit. So there are five main attributes: the average temperature, maximum temperature, minimum temperature, humidity, as well as the rainfall. Let's look at the rainfall. Most of the time during the year, most of the days are just very little rainfall, and you can see a skew towards to the right. There are some cases where there is extreme rain, some with 400 mm accumulation, and these are plots from the weather stations in Malaysia on the distributions of the rainfall along the year. Similarly, if we look at the temperature data, this is the average temperature, and you have the maximum temperature as well as the minimum temperature. And if you look at them, you can see a little bit of seasonality here, where you can see it's fluctuating up and down. And also we have the last one, the average relative humidity, which is also having some sort of seasonality as well. Alright, that's all for the exploration. It's quite self-explanatory. We'll jump into the feature transformation. On the CPO prices, since we are predicting the price, we just want to give some attributes where it can learn those features easily, like the moving average of the price using 5 periods, the volume, the moving average of the volume, as well as the change for 5 periods and 10 periods. And basically drop everything that have NAs, and as well as just picking up a few columns. We drop the rest of this, but we only pick like the price, the moving average of the price, volume, and change for our CPO price data frame. For the production, we create feature for monthly production change. We are not exactly predicting the production, we are actually predicting the change in production. So that's why we are using a diff function here to get the production change on a monthly basis. And if we look back at the production plot, you can see there is some sort of seasonality as well. Like usually in the beginning of the year, it has a dip. So this is why in our feature transformation, we also created an attribute called month to just see if it's important at all. Moving on to weather data, if you remember, the distribution of the average rainfall is highly skewed towards the right, and there are a lot of large value towards the right. Like if you look here, there's actually values around 400, 200, and so on. So we want to make this value small for the model to learn easily. So we're using a scaling factor by using a log x plus 1 to scale the values down. So right now, from 400, we actually lower it down to like around 5. So this is good enough. Then we visualize the weather data. The distribution for the temperatures and the humidity are as such. You can see that the maximum temperature and the minimum temperature are not so nice. Basically, after this, we're just gonna drop these two because we can see that they are highly correlated. So the humidity and the average temperature distribution is very nice. We keep it as such. And going to the correlation, as I have said before just now, we can see correlation between the temperatures, the T max, and T minimum. These are positively correlated as expected. And we have the humidity here, which is negatively correlated to temperature. And then we have the rainfall, which doesn't really look like anything. So what we do next is we do a transformation by pivoting the tables. So we pivot the tables for creating features on columns for every station. So we have the humidity for this station 486,000, the humidity for this station 486010. Similarly, we do it the same for the temperatures and as well as the PP, which is the rainfall. Then this is our data frame for the weather. Next, we look at the news data. The news data is scraped from the edgemarket.com. Since we do not really want to label the data ourselves, we just use off-the-shelf open source sentiment analysis package called the weather sentiment. You can look it up yourself, but apparently it's a pretty good package by CJ Huto on the GitHub. This is the link, and it's a very easy installation. You just keep install, and then basically you can run it just like that. So what I have here is just from weather sentiment import sentiment intensity analyzer, and what I do is just call the function here, the polarity score x, and it will return 4 attributes: negative, neutral, positive, and compound. Compound is a combination of the 3 score here, where I aggregate the score into something that is like a scale for these 3 attributes. So we do a quick check here for the sentiment result, and for this news title, It says EU palm oil ban is Indonesia's concern for Axiata Telenor merger. So I can interpret this as a negative, and let's see what does the weather sentiment cause it, right? So we can see the negative score is positive, and there's no positive score here. So the compound score is negative because of the negative score here, which is expected. Okay. And what we want to do is to group this sentiment by date, because there are multiple news cycles uh, for different days, and you can see here for the same day there are multiple news cycles. So we want to aggregate them into just a single day, and we want to aggregate the score to a single day as well. So what we do is just simple mean aggregation by date, and what we do next is just do a rolling sum of 5 periods to just smooth it out a little bit better. And we look at a pair plot for sentiment attributes after the feature transformation. You can see that the positive attribute is positive correlated to compound, as well as the negative is negative correlated to the compound attribute, which makes sense. The neutral attribute is just there. Once we have all this feature transformation done, we want to merge them into data frame for our model. I've set up 2 data frames. One data frame for the prediction of CPO price. So in this data frame, we basically merge the price data frame, the production data frame, and the new sentiment data frame. And the product of that is something like this. Actually this. Because then we have the production change, the month, the day of week, as well as the sentiment attributes here. And the first part here is just the price, where we will do a prediction on the price. The second data frame, we merge the production data with the weather data. So basically we have a bunch of attributes of the weather for different weather stations, and at the front we have the production change as well as the month. So we now move on to the most interesting part, which is the modeling. For the modeling of CPO price, we are using TensorFlow. We are using LSTM actually to do this task. So we want to partition the data set, and since we do not want to shuffle them because these are time series data, what we do is just a simple train test split with all the attributes inside. And what I do here is I say I want 1/3 of my testing data to be 1/3 of the data set to be my testing data. So I have something here that say split the training data at 1 minus 0.33, which is like 2/3 of the data set. And here again I just plot out the attributes for easy visualization, and you can see other than the moving average of the price, nothing else really correlates very well to the price attribute. So I would have imagined this will be a very difficult task to predict the price from these other features. Then we normalize the dataset using a simple z-score normalization, and we go into the LSTM model config. So we set up our training data and the validation data, also our testing dataset, and we just declare all the fancy stuff here like the batch size, as well as how we want to fit them into our model. So for our model, we create it using a model sequential. We have a single layer of LSTM with 64 neurons, and we added dropout as well 2 times because we want the model to not overfit quickly. After LSTM, we have a dense layer as well with 64 neurons, And the final layer is the output layer with just a dense single neuron, and we call activation of a linear activation function. So I've done some testing on this, and I found that 65 epoch is actually the best. Optimizer, I was using NADM. NADM is just an Adam optimizer with different momentum. So the N actually stands for something called, let's see here, if I remember correctly, it's called Nesterov. Yeah, so NADM is just Adam with Nesterov momentum, and I find it to perform better than Adam optimizer, as well as the other like IMS prop, as well as ADA delta. So this is the best so far. The loss function, we are using mean absolute error. And so once that's done, we train it. This is the training and validation loss chart. You can see very quickly, like within 20 epoch, it already tends to overfit the data. So we just cut it at 60 because the validation loss is not improving. And at the end, we get a validation MAE loss of 0.17. Okay. And after that, we just basically plot what was predicted by the LSTM. This is just predicting the next day close price. And you can see it's doing actually a pretty good job at predicting the close price. But what we really want to know is what features are important in predicting this closing price. And so what I've done is using some feature perturbation. This is just basically going into the columns, setting the column values into something else. You can shuffle them, you can set them to 0, and see the effects on the prediction score. So what I've done is just I replace the columns values to 0 one by one here by putting them in a loop, and I predict the data set again using those changes and get the mean absolute error from that and compare them. So doing so, it gives me the feature importance based on the highest difference of the metric used, which is the MAE. And we can see here the price is actually the main feature that is helping the LSTM to predict the price of the CPO. So the first three attributes are price and the moving average of the price itself. And then the rest you can see is pretty much not very relevant. I would expect that the new sentiment would give a little bit higher, but no, not even the month or the production change or even day of week. So I would say none of the features in the hypothesis that we wanted to change the CPO price is actually significant. Next, we move on to modeling for the CPO production. Here, before that, we just do a simple standard scalar, the z-score normalization on all the columns, as well as on the production change itself, except for month, because month is a categorical attribute. So here we partition the dataset into X and Y, and we have 4 different models that we are using. We are using a support vector regressor, a random forest regressor, a k-neighbor regressor, as well as the last one, which is an ensemble of all 3 by using all 3 models in a voting regressor. So we initialize all these models and we evaluate all these models using a 5-fold cross-validation. The metric used here is actually mean square error, and yeah, just feed the data, predict them, and I have the plots here where we have all the metrics uh, printed out, as well as the how well it fits to the testing data set on each fold, each of the 5 fold. So as you can see, on the first one, on the first fold, the random forest has actually performed the best, and the voting classifier is like the second in between these three. And then moving to the second fold, now instead of being the best like in the first case, the random forest is actually the worst case, and that is not something we want because we want the model to be robust and perform well every time. So what happened is you can see the metric for the models varies a lot between different fold, right? Like it was 0.63 just now, it's now 0.88 for random forest, and then it was 0.94, which is worse, and so on. And what we want to do with this is we have a voting classifier, which is an exact ensemble of these three classifications, and it will basically give a more robust prediction. It's not always the best prediction, but it will always be the most robust one, and it won't be as bad as the worst classification that is in the group of classifications using. So for example, like this 0.65 is actually pretty decent prediction from these three of them, where the best one is 0.54, and this is just like 0.1 off from the 0.54, and it's not the worst like 0.78 from Canon. And in this case, on the fourth fold, it's actually beats all the other three classifications by having a 0.9 MSE, while the rest are actually higher than that. So a voting classifier is a very good way to making your model robust without having too much tinkering with your models. The trade-off is only the computational time, because it's actually running three models at the same time to give you a prediction on the voting classifier. Okay, then the most important part of this is the feature importance. Similarly to what we used just now, which is perturbation, we are just right now directly using permutation importance from sklearn. And as you can see here, we have the month being the most important feature, and the rest of them are made up of mainly rainfall and humidity, average humidity. So what we can tell from here is that the temperature isn't as important as rainfall and humidity, and the month is actually the most important because the month has a seasonal effect on the climate. So it's actually a more reliable way of predicting the production of CPO. Okay, this will be it for our milestone 4 this time for this episode. The next time we'll be trying to put things into development, like deploying it in a Flash app or Kiwi mobile app. So that's all for today. Thank you.